Event propagation with microservices using Pulsar and change data capture. I'm Eyal Gutkind, and I help Scylla users to use Scylla. My team and I help migrate workloads from different platforms into Scylla on a daily basis. Our team understands that provisioning the database correctly will remove future challenges and allow builders and application developers to spend more time on their application rather than on their database. And with that, I'll let Mahi introduce himself.
Hey everyone, I'm Maheedhar. I'm a solutions architect here at Scylla. I've been working in the data and messaging queuing space for about 9 years now. So just very excited to be here and learn about new developments and also talk about newer developments from Scylla as well.
I think Mahi, you control the slides.
All right. So yeah, go ahead, Eyal, from here. I mean, you can set the agenda, and from there onwards, I'll take it from there.
Sure. Can you move to the agenda slide, please? I don't control the slides.
All right. We should be on the.
We are. Oh, there you go. I was going to say we're just about. Yep. Now we're on the agenda.
Okay. Thank you. So here's a brief agenda for today's talk. First, we will begin with the high-level overview about Scylla and the open source framework Seastar, on which Scylla is built on top of. Next, we will dive into how message queues and Apache Pulsar are enabling the streaming first architectures. We will then explore how message queues and change data capture are enabling microservices. And finally, we will dive into the details of Scylla's change and data capture, how it's implemented, how you can get started with that as well. Towards the end, we will take some questions. Please post your questions in the Q&A button window, and we'll get them there. So if you can move to the next slide. So a little bit about Scylla. Can you move to the next slide? We are the team behind Scylla, the real-time big database. Scylla is a drop-in replacement for Cassandra and DynamoDB-based applications, but with 10 times the performance and predicted low latencies. We are available on the cloud and on-prem with both open source and enterprise editions. If you haven't already, I really, really encourage you to go and try Scylla today. Next slide. Now that you understand a little bit about what we try to do, so let me explain what the benefits and the design decisions that we took into our hand when we designed Scylla. So first, we wrote Scylla in C++, which results in a faster performance, lower latencies, and much more efficient use of your hardware. Scylla has a shard per core isolation architecture, which each Scylla shard is associated with a CPU core. Also, the necessary RAM is allocated by the shard as well. This ensures that when you run your application, you never starve of resources. Everything is async on the platform, so there are no locks. Scylla also runs on XFS, so we get the performance benefit of using a very asynchronous file system to our benefit. Scylla comes with its own integrated cache, which is optimized and auto-tuned for your specific workload. So no need to worry about key caching, row caching, Linux caching, on-heap, off-heap. We don't care about those. Everything is auto-tuned on our side from the caching perspective. Scylla is built on top of an open source framework, which is called Seastar. We will a little bit talk about it in a few seconds, which orchestrates both task IO and disk IO scheduling. And we will go, as I said, a little bit more into that one as well. Scylla is an autonomous database, which means your administrator can get the benefit with minimum tuning. You don't have to tune all different parameters for a specific workload. Scylla understands the workload and tune itself and make sure that you get the benefit of using those resources that you have in the system. Next slide, please. So as I mentioned before, Scylla is built on top of an open source framework, which is called Seastar. Scylla self-optimizes itself to use that framework. Since we know the performance capabilities of the system you're using, Scylla will leverage the entire architecture and control theory and use control theory algorithms to ensure that memory flushes, compactions, and repair are in check, meaning they are not overwhelming your system and preventing you from using it. That avoids and minimizes any latency spike you might see on your system, so that your application writes and reads are always having the priority over other workloads. The internal controllers will also prioritize the front end workloads over the back end workloads and make sure that Scylla provides the best latencies on the user side. Also, on times when your application workload is lower, we will prioritize then the back-end office processes to make sure that we comply with the needed compaction, memory flushes, and so on. Next slide, please. In terms of compatibility, ScyllaDB users benefit from Scylla's full compatibility with Cassandra and Cassandra ecosystem. We also support DynamoDB API today, and the ecosystem components listed here, like Spark, Kafka, Pulsar, KairosDB, and many others, and Presto, will just work out of the box with Scylla. It means that you can connect your current application with your current third-party or auxiliary system to Scylla and get the benefit. In addition, there are many client drivers available in a variety of programming language that can be used as well, so you don't have to change your application. Scylla has created and optimized drivers for developers using Java, Go, and Python, and these optimized drivers can better take advantage of the sharper core architecture of Scylla and Scylla Enterprise. From here, Mahi, take the discussion.
All right. So yeah, let's jump a little bit into the details of Apache Pulsar and the message queuing systems. As most people know, Apache Pulsar is open source distributed PubSub messaging system, originally created at Yahoo and now part of the Apache Software Foundation. There are multiple applications which tend to be built on top of the streaming and message queuing systems. Let's dive into how message queues and streaming are enabling modern applications. And how event streaming is becoming a very crucial part of the infrastructure for a number of real-world applications. Platforms like Apache Pulsar are highly available and resilient to node failures and automatic recovery. These features, a number of features which we're going to discuss, at least at a high level, enable Apache Pulsar to be an ideal sort of candidate for communication and integration between components of large-scale real-world systems like Splunk and Hadoop and various microservices and various data warehousing services, which enable real-time inventory, real-time fraud detection, real-time customer 360, machine learning models, and all the different contextual event-driven applications. So here, I don't know if somebody has already gone through it, but here is a recent white paper which was published, which, where the different components of or features of Apache Pulsar platform typically consists of PubSub, functions, connectors, Pulsar SQL, and various integrations like Flink and Spark and Kafka and Pulsar. So all these different features basically enable these applications, and a survey which was done recently sort of gives you a spread of how all these functions are being used, whether it might be ETL, application monitoring, or various applications which are being built, or various core business applications or machine learning or IoT-backed applications which are being built. The most common one seems to be various asynchronous applications, which typically consist of various microservices. A lot more detail is available in the URL that I've listed below. So now let's dive into how various message queues are used and how they're used by microservices and how change data capture plays a role in this. So, different types of microservices which are typically built, various design patterns, or whether it is a stateless application. If it is a stateless application, typically it's ephemeral in nature, just comes and goes based on demand. Typically this is used for various application tier microservices, so whether it's for converters or translators, or so there's no dependence on other microservices. So it's sort of like a self-contained bounded context which is created for it. And also there's no local data storage disk IO which is needed for it. So since there's no shared state and are easy to replace and very easy to scale up and scale out, those kind of microservices are stateless typically. And the next type of microservices is persistence. So persistence are durable. These microservices are durable in nature, which typically depend on databases of some sort. They use local storage, whether it is for reads or writes, and they're a lot disk dependent. They're possibly built on a single VM or a one rack unit. These are typically applications which are used for your system of record, your source of truth. They're relatively easy to scale for reads, and you can also employ some CQRS, like command query responsibility segregation, where the data and how it is written and how it is read can be two different ways, and typically message queues plays some important role for that. And also there's no cross-service or two-phase commits typically in these sort of environments as well. The next pattern would be aggregator pattern. Typically this is used for workflow choreography or workflow orchestration. So it depends either on multiple microservices and not just a single microservice. So it depends on a particular workflow being orchestrated where an event comes into one microservice and then it needs to be transmitted to another microservice, either the entire record or some parts of the record. And sometimes some parts of this record also needs to get transformed and then passed on to the next one, or sliced or translated and then passed on to the next microservice. Typically this is used for, there's sequential or parallel calls for different microservices, well, aggregator patterns. A lot of times timing is everything for these type of patterns. And also it's sort of easy to scale independently, but practically not always it's the simplest thing to do. We'll go into how CDC plays an important role in this particular type of pattern, especially the aggregator type of pattern. So the most common use case is when you are feeding or propagating events from one particular microservice, which is backed by a particular bounded context by a particular database. And the data goes into, let's say, Scylla in this example. And then data can be either propagated to, typically is propagated to a message queuing system. It could be a Pulsar, Kafka, it could be a simple RabbitMQ. It depends on the context and the scalability which is needed. We believe systems of the scale of Pulsar and Kafka could really sort of enable this. Typically when an example in this case would be an event comes in and some part of this event needs to go to some sort of a monitoring system for fraud detection, or needs to go for search or Spark or a data lake for eventual long-term storage. These sort of message queuing systems is a fairly common pattern where you would see this. But the unique part of this is the CDC stream, which is transmitting only parts of the data. Now, so you don't need the whole data set. You just need some part of the data so you can reduce your overhead on these downstream systems. So that's where you could use something like Pulsar functions and things like that, and then sort of transmit rest of the data. You would also need a connector for something like this, which Scylla is also looking into publishing. A Pulsar connector as well as a Kafka connector. I mean, the standard examples for use cases like this are like top 10 results in gaming or leaderboards, or top 10 active sensors. These are the type of use cases where you tend to use something like this. Another use case where you can do is a low coupling replication. So this is sort of a scenario where if you don't have much traffic and you just want to use just the CDC stream, then you can, CDC stream is typically at a table level, not at a key space level. So you can set which tables you need replication for. And then the corresponding CDC stream can be replicated from one DC to another DC. And the second DC could be supporting a separate bounded context from a separate application. So that gives you the benefit of not having, this is for a low volume system, but for a high volume system, we highly encourage you to use a message queuing system. So another small example here, another small detail here, which we already spoke about is if it is multi-DC based sync using Scylla versus a CDC based sync. Typically it's at a table level. The consistency is, it's sort of weak, and it depends from use case to use case. Certain use cases, this might be okay. But if you sort of need a strong eventual consistency, that's when you use a multi-DC. But if you want to use CDC-based sync, sometimes it's weak. And also you can use it for two distinct clusters, whereas for multi-DC, you have to use it for a single cluster. So if you have multiple microservices in an aggregator pattern, then you would tend to use CDC-based sync backed up by a message queuing system if you need high volumes. And data can be different in different replicas, and you're able to massage the data using things like Pulsar functions or Scylla agent as well. So now let's dive a little bit deeper into how Scylla's change data capture is built. And I'll also give a few examples so that I can, make this examples really simple to digest and understand. So we recently released a new feature called Change Data Capture, or CDC, not the Center for Disease Control, but Change Data Capture. Basically, this captures and keeps track of data that has changed. It can also help with mirroring your database, replication and state propagation across various microservices. It is configured per table and with limits on the amount of disk space to consume for storing the CDC logs. We co-locate these CDC log partitions along with the base table partitions. This is a very unique feature. So when you co-locate the CDC log partitions along with the base table partitions, this tends to improve your performance significantly when you compare it with other CDC implementations of Cassandra or Dynamo. I'll go into some of the benchmarks later. There are a variety of configurable options that help you configure the stream of the change log. You can choose to have either the Postimage that is only the change state, or just the delta, that delta is just the changes made to the columns, or you can also stream the pre-image that is the previous state. And so basically all these different states, I mean, I'm going to give you some examples as well, but it's a very configurable options which are available. And if you all are also interested, when you get the slides, you can go to the link which I referenced in the bottom, which explains a lot more as well. And also we are releasing a Scylla CDC Kafka source connector soon. So this should really help, streaming out the changes to a Kafka so you can integrate various microservices or KSQL parameters or Pulsar functions, whichever sort of transformations you want to apply, whether it might be a single message transforms or a transformation for a stream of events which is coming in. You can apply all the transformations and then send it to downstream systems. This typically tends to greatly optimize your workflow, and you should see orders of magnitude savings in terms of cost as well as in time, which tends to really benefit. So let's take a few examples and then go into this. Typically, this is a standard example where you have a company key space and a bunch of employees which are part of it. You also configure this typically with CDC as well as a few parameters which go as part of the CDC initiation which you're doing. So let's say you're inserting into the employees key space, employees table, a few values: production Smith, John Smith, and age 35, level 2. And you're opting to get only the deltas. So what that tends to give you is it transmits this particular delta value which you've inserted. And let's say now you insert another value, Elizabeth Green of age 50 from marketing. And then you're opting for delta, then you tend to see just the delta value here, which is emitted downstream, whichever subscriber is subscribed to these changes. Now you're running CDC still in the delta mode, but then you update John Smith to level 3. Let's say John Smith got promoted. And then you're subscribing to the delta, so you get the partition key, which is John Smith and the department production, and also you get the delta, which is level 3. Now let's say you delete, John Smith age. You just delete not the entire record, just the age column. So then a tombstone gets set on that particular column. And then if you subscribe to the delta, then you tend to get the primary key, which is John Smith from production department, and the tombstone for the age column. Let's say now you're running CDC in pre-image mode, and then you insert John Smith, age 35, level 2. So since you're subscribed to the pre-image, you just get an empty record, a null record. But if you're subscribed to the delta as well, then you get John Smith, the production department, age 35, level 2 as well. Now you update this particular record to level 3. And then if you're subscribed to the pre-image, you will get John Smith from production department of level 2, because that's what the record was there before. But if you're also subscribed to the delta, then you're going to get John Smith from production as well as the delta, which is level 3. Now, let's say you delete the record, John Smith, you delete the age. So a tombstone gets set there, and then if you're subscribed to the pre-image, you get John Smith from production of age 35, But if you're subscribed to the delta, then you get the tombstone as well as the partition key. Now, if you delete the particular record, then the record is gone. But if you subscribe to the pre-image, the downstream system which you get is the deleted record. And if you subscribe to the delta, you get the partition key as well as the tombstone along with it. And then now you're running CDC in Postimage mode. When you're running it in this mode and then you update the record, you set it to level 4, let's say. So it gets level 4. And if the delta which you get is level 4, and the pre-image, the particular pre-image which you set actually should be here, it should be level 2. Now
you subscribe to the post image, so you got the post image record and the delta if you're subscribed to the delta itself.
Yeah, thanks for correcting me that. Yeah, since you're subscribed to the post image, then you're getting level 4 as the post image record, as well as the delta would be just 4. Yeah. So next, if you're subscribing to the post image and you delete the record, you delete the age, then the post image which you get is the primary key as well as the level, and you also get the tombstone. And if you're subscribed to the delta, then you get the tombstone and the primary key. So now you delete the entire record and you get a post image, which is the primary key with the tombstone on it, and the delta, which is the primary key with the tombstone on it. So these are like various scenarios where I've given you I'm sure plenty of examples. Here's how you would enable CDC. If you want to try it, you can download Scylla, change the Scylla YAML file, you enable the feature currently is experimental. In the next release, pretty soon it's going to go GA. And typically you can, once you bring up Scylla, you can simply create a table with CDC enabled, or you can even alter a particular table with with the CDC feature enabled. And these are various options which you can, modes in which you can run CDC, and various options which you can provide. Enable true, pre-image, post-image, delta, as well as TTL. That's another unique feature where you can just simply supply the TTL on this on the particular record, and then when you insert with a certain TTL, and so you don't have to worry about cleaning it up. The record gets automatically cleaned. These are all the various things which you would typically look into when you're creating a table. So when you created the company key space employees table, you pass in all these for all the different parameters which you want. And you created a primary key, which is the composite of department, last name, first name. And then you pass in all the CDC parameters which you want. So with CDC enabled and the various features that we like, whether you want post image, pre image, or the delta, as well as TTL. Those are the parameters which you would pass here. Then seamlessly, without you doing anything, the necessary CDC log table gets created, which is a very unique feature of Scylla. You wouldn't really get this in Dynamo or in Cassandra. Excuse me. So. And typically this gets created with a particular partition key, which is the stream ID, and all the particular records which I mentioned, they all get created here, as well as all the different parameters, sort of records which get created. They also get created with the Boolean flag where to see if it is deleted or not. And if it is deleted, then this particular Boolean flag gets enabled so that you don't read the actual record and the tombstone gets set. And here you would, it would get automatically created with, this is a special key which gets automatically created when you created with the partition ID, which is the stream ID, as well as the time of the record, as well as the batch sequence number, which it gets created with. So here, this is sort of a workflow, a particular sequence diagram which explains how the entire thing is orchestrated. It's fairly simple. So when you write it, let's say you're writing with replication factor 3 as at a consistency level 2. So then the coordinator pushes the write, the client pushes the write to the coordinator, and the coordinator sends it to replica 1, replica 2, replica 3. And at the same time, there's a CDC Write, which gets sent to replica 1, 2, and 3. Then you get 2 acts. Since you committed it with quorum level 2, then you tend to get, once you get the consistency level, the client moves on. But in this case, it also gets an ACK from the CDC log, which gets created. And once the CDC log, you get a consistency level 2, you get an ACK as well to the client. And then the client confirms that, both the write into the base table as well as the CDC log into the CDC log table are acknowledged, and then the client moves on to the next record which needs to be inserted. So there's a fair amount of overhead because of this extra acknowledgements which are needed from 2 other replicas, and we've benchmarked this. I'll share the benchmark results as well. So once and eventually you get an ACK for the 3rd replica as well as the 3rd replica of the CDC log, but the client doesn't wait for it because it's an eventually consistent system. So there's another very unique feature of the CDC log which we have discussed. Basically when data, and this is very specific to Scylla. So Scylla doesn't only care about records at a node level. Scylla cares about it at a CPU level, which we call shards. Basically when a record gets inserted into all the 3 replicas, the CDC log also gets created on the same shard or the same CPU core, which gives you a tremendous performance boost when compared to other systems. But still there is an overhead because of creation of it. And we've created, and this is a small sample data set which we created, and here are the benchmark results which we got from benchmarking this. So the throughput reduced by, so when CDC is disabled, you can see it's about 78,900 operations approximately. And when you enable Delta, then you get about 21% decrease in the throughput. When you enable Delta as well as pre-image, you get about 58% decrease in throughput, as well as the latencies increase by 23% and 130% when you enable Delta plus pre-image. And the 99 percentile latencies typically with CDC disabled, if it is about 3.6 milliseconds. With Delta, it's about 4.7 milliseconds, and Delta and pre-image gets about 9.3 milliseconds. So there's significant overhead because of enabling CDC, but in the grand scheme of things, like the benefit which you get from making this completely automated and streamlining your microservices pattern is considerable, because you don't need to invest any engineering time in maintaining any of this.
There, I just want to quickly interrupt and just let you guys know we have about 5 minutes left.
Yes.
So I just want to make sure you guys are conscious of that, and we have some time for Q&A.
Sure. So it should be done in a minute.
No worries.
So here is an eye chart which compares Scylla with Mongo and Dynamo and Cassandra from a CDC standpoint. There's significant benefits which you see And here are some takeaways. Basically, the benefits of the aggregator microservice pattern to using CDC in Scylla is tremendous. And it's easy to integrate and consume with plain SQL tables being available. There is reasonable overhead, but when data is replicated in the same way as normal data, as the base table data, the writes to the same replica ranges go to the same shard, and they're combined together. So there's significant performance benefits because of that. And there's, if your consumer fails to act, it doesn't overflow. The logs can be automatically handled. And data is also TTL'd in a very seamless way. If you want to try Scylla CDC, I highly encourage you. Use the experimental flag, and you can try it. There's a nightly build which gets released every day, so you can use that nightly build on your Docker hub. And also there's all the documentation which is available as well. So that's it from us today. I would love to take questions now.
If you want to take a look at the Q&A chat function, you'll see some questions in there.
Okay. Okay, here, I do see them now. Okay, so so there looks like 1, 2, 3, 4, 5 questions there. So we might be able to take as many as we can. So is the Scylla CDC Pulsar source connector on the roadmap? So Eyal, do you want to?
Sure. So we do have a source connector for the Kafka on the roadmap. I don't know if we have the full Pulsar integration out there yet, but it's definitely something that we should look into it.
Okay. So does Scylla CDC include blob fields? Yeah, I'll take that question. So Scylla supports 4 different basic data types, blobs. Scylla supports the primitive data types, all the primitive data types, as well as UDTs, typically frozen data types, as well as collections. Very limited set of collections, not a whole lot, but Scylla supports a few collections. These are all, and CDC is based on these, on the base table, so it should be supporting all these. What is the current integration path between Pulsar and Scylla? Pulsar as source, as sink. So I can take that. So as Eyal mentioned, we have integrations with Kafka sync connector, as well as CDC source connector. But since we have Kafka on Pulsar API available as well, so more than likely it's going to be compatible. Would you categorize a microservice that utilizes a distributed cache, such as Ignite, as durable or stateless? So Apache Ignite is sort of an in-memory fabric which is replicated, but it's in memory only, so, and it's probably backed up by disk. Since it is backed up by disk, I would think of it as durable. Things like two-phase commits, or if you want a full-fledged system, then I wouldn't call it durable. It would be stateless, but it is backed up by disk, so you're not going to lose your data. And also, if you need to expand your data, since it is built on top of a distributed hash, data needs to get redistributed as well. So that's also another thing which I would call it as durable and stateful instead of stateless. The next question is, are the CDC transactions then streamed via queues to other systems to then process? Yes. So when the data comes in into Scylla, or through a microservice, it comes to basically your landing microservice. Different people have different names for that. Once the data comes into your landing microservice, then you either stream out the entire data, or you can stream out just the particular changes which you're subscribing for running CDC in a particular mode. And then data can be pushed as using a source connector into a message queuing system. And once it's pushed into a message queuing system, then all the subscribers which are subscribed to it can pick up that, and then you can apply transformations, functions, or KSQL, whichever system which you're using to transform the data and then send it down to a downstream microservice. How is the CDC table cleaned? Yeah, go for it, Neil.
So basically, you can TTL the data. There are TTL settings that you put on each record. So once if the user is not consuming the resources, at the end of the day, he might lose the data of the changes. But in regular operations, data is going to be TTL'd on a different period. So this is how the data is not overconsumed and the data is cleaned out completely. If you want to add more on that one, Mahi.
Yeah, so TTL is per record. Whenever you're inserting a record, you tag a TTL along with it and then insert it. And then when that TTL expires, you get a tombstone gets set on it, and then it gets automatically cleaned up. That's sort of like the standard way you would get rid of a CDC log. This is very similar to the base table as well. So this is very unique implementation of Scylla when you compare it with Cassandra or most systems. So we treat the CDC log pretty much as if we would treat the base table. So that's how we clean up the CDC table. Okay.
I think we have no more questions.
Awesome. Thank you so much. And for everyone else that's still tuning in right now, we'll have about an 8-minute break before our next session starts.